So today we're going to find the atomic packing factor of a simple cubic lattice. So first we're going to find the number of atoms per unit cell in the cubic lattice. In this unit cell type, atoms are only present in the corners of the unit cell. Here each atom contributes 1/8 of its volume at each corner. Since there are 8 corners, we will multiply that by 8, and we will find that this adds up to 1 atom per unit cell. There we go. To find the percentage of the total unit cell volume occupied in this cubic lattice, this is the equation that we're going to need. V prime over V times 100%. Now, V prime is the volume of the atom, which we will assume is spherical. So we'll write out the equation for the volume of a sphere. 4/3 times pi times r cubed. R is the radius of the atom, and as we see here, that's going to be about half of the length of the side. So let's actually use this equation instead. 4/3 times pi times a/2 cubed. And we're actually multiplying this entire value by 1 atom. So the V is just the volume of the cube, and that's going to be a cubed. So now let's put it all together. 4/3 pi times a/2 cubed. We can omit the times 1, all over a cubed, and we'll multiply that by 100% to get the percentage. Now if you type this into a calculator, you are going to get 52.36%. So this just means that 52.36% of the overall volume of the cube is occupied by the atoms. For a body-centered cubic, we now have an extra atom in the center of the unit cell. So just like before, we'll count our 8 corner atoms, and we'll add that to the 1 center atom, and that gives us 2 atoms for this unit cell. The volume of the atom, just like before, is 4/3 pi r cubed. Now we need to find the volume of the structure as it relates to r. I redrew the structure so that we can see the geometry more clearly. We need to take this right triangle here at the bottom, you can see, and I'll redraw it up here. With these sides being A, and the hypotenuse we'll call L. Using Pythagoras' equation, we see L squared is equal to A squared plus A squared. We also need to look at this triangle here. And I'll redraw that one too so we can see it. And we see that the side here is A. The side at the bottom here we called L. So we have A and L. And the hypotenuse we'll call D. D is the longest distance inside the cell, and it's equal to 4r. And we can see that if we look over here, if we take this radius, r, and in the center atom, we take the entire diameter, and we'll just call that 2r. And we take the radius for this atom here, r as well. We add those all up, and we see that the entire distance from corner to corner is 4r. So here we have L squared plus A squared is equal to 4r squared. Now we already established L to be A squared plus A squared. So we'll replace our L value with that. We have A squared plus A squared plus A squared equals 4r squared. And let's clean this up a little bit here. And we can rewrite that up here as 4r squared is equal to 3a squared. Now we take the square of both sides, we get 4r is equal to square root 3 times a. Or a is equal to 4r over square root 3. So now we have our a. So just like before, we have our equation for the sphere. And our equation for the volume of the cube, which is a cubed. Multiply that by 100%, and you type that into a calculator, you'll find that 68% of the total volume of the cubic lattice is taken by the atoms. Now for the face-centered cubic lattice, we see the same 8 atoms on each corner, each one being 1/8 of the way into the structure. But now we have to account for the 6 face atoms, each one being halfway into the cube. So 6 times halfway in. Add those up, and we get 4 atoms for this structure. Let's find the radius of the atom, but first we need to find the hypotenuse of this triangle. Right there. We know that this is A on the side. So if we draw this triangle out here, we see that the 2 legs are both A over 2. And we'll call the hypotenuse D. So D squared is equal to A over 2 squared plus A over 2 squared. Taking square root of both sides, D is equal to just the square root of A over 2 squared plus A over 2 squared. And that's going to give us square root 2 times A over 2. To get the radius of the atom, the radius is just going to be D over 2. So square root 2 times A over 2 all over 2. And that's going to give us square root 2 times A over 4. And this is going to be the radius of the atom. Now we can plug in our values for our main equation. We have 4 over 3 pi times r, which is square root 2a over 4, and remember that's all cubed, over a cubed. And the top portion here we're going to multiply by 4 because of our 4 atoms. And then the multiplying by 100%. Now this is going to give us 74%, and you can verify that with a calculator. So 74% of the space within the unit cell is occupied by the atoms. Now lastly, let's look at the diamond lattice structure. Now this one's a bit more advanced and the structure is kind of hard to draw, so I just found a picture. You may also hear this structure called the zinc blende structure. And when it's called that, it means that there's more than one element involved. So like if it's silicon carbide or gallium arsenide or some other semiconductor combination of elements. So here in the structure we have the 1/8 atoms at each of the 8 corners. We have the half atoms at each of the 6 sides. And we also have 4 whole atoms that are just floating around in there. So if we add all that up, we find that there are 8 atoms total in this structure. Now let's find the radius of the spherical atom as it relates to A being the side of the cube. So the triangle we're going to use for this is going to look different from the others. We'll use 3-dimensional coordinates to find this. So starting from one of the corner atoms, the nearest atom is 1/4 of the A distance in the x direction. So that's about 1/4 A. And same deal in the y and in the z direction. So we get kind of that shape there. And each one of these sides is 1/4 A. The distance here, and I'll draw this out here so we can see it a little bit better. So it looks kind of like this. Okay. And this is going to be in the x direction, in the y direction, and in the z direction. So the distance here between these 2 atoms is going to be 2r. And this is because we are using the standard hard sphere model. These nearest neighboring atoms will just have the distance 2r. Now we'll use the 3D Pythagorean theorem. We have 2r is equal to square root 1/4 A squared plus 1/4 A squared plus 1/4 A squared. And if we type this into a calculator and solve for r, we're going to get that r is equal to square root 3 times A over 8. Now we have what we need to find the percentage of the space occupied in the unit cell. We have our sphere equation for volume. And for R, we're going to use our value we found before, cubed. Multiply this by the 8 atoms and divide this whole mess by A cubed times 100%. we find that this is going to add up to 34%. 34% of the unit cell is occupied by the atoms. Amazingly, this is much less efficient than the other three structures. Yet, this is the structure of diamonds, one of the strongest natural materials you'll find in nature. When you have this diamond structure composed entirely of carbon atoms, like in a diamond, the atoms form a four-way tetrahedral bond. And these are also covalent bonds, which are very strong. When you have other elements in this structure, such as germanium or silicon, the structure will actually be very weak. I hope you all got something out of this explanation. I know there are plenty of videos out there explaining the cubic lattice structures, so hopefully I was able to shine a new light for you on this topic. Thank you all for watching.